In this lecture, we are going to talk about maybe the most important interview question as far as one-dimensional arrays are concerned. So we have a one-dimensional array of integers, and the problem is that we would like to design an algorithm that's going to reverse the order of the integers within this given array, and this algorithm must be in place, which means that we have to design an algorithm without any extra memory. So what do we have to do? We just have to use two pointers, two variables, the start index and the end index. At the beginning, the start index will be pointing to the first item of the array. The end index will be pointing to the last item of the array. What do we have to do? We just have to swap these items. So 5 will be 1 and 1 will be 5 accordingly. Then we have to increment the start index and we have to decrement the end index. Again, we have to swap the values, so 2 will be 4, 4 will be 2, and again we have to do it until the start index is not smaller than the end index. So in this case, both start index and end index are pointing to the same item, which means that the start index is equals to the end index, and this is when we know that we have to terminate the algorithm, because as you can see, we have managed to reverse the given array with an in-place algorithm. There is no need for extra memory. Let's take a look at a concrete implementation. We have a one-dimensional array of integers. We have two pointers, the start index and the end index. The start index is pointing to the first item of the array. The end index is pointing to the last item of the array. While the end index is greater than the start index, what do we have to do? We have to swap the two items and we have to increment the start index and decrement the end index. And finally, we can return with the reversed array. So it is going to be a linear running time algorithm, because as you can see, we just have to make n divided by 2 iterations. Of course, as far as complexity analysis is concerned, we don't care about the constants, so it is going to be linear running time complexity. And as you can see, there is no need for extra memory, which means that it is an in-place algorithm. So if we run the algorithm, the input is 1, 2, 3 and the output is 3, 2, 1. So we are able to reverse the given array. What if we have just a single item? Okay, it is working fine. And what if we have, for example, 4 items? In this case, it is working fine as well. 4, 3, 2, 1. So this is how we reverse an array in ortho and linear running time complexity with an in-place algorithm. Thanks for watching. In this lecture, we are going to talk about the anagram problem. So first of all, what is an anagram? An anagram is a word or phrase formed by rearranging the letters of a different word or phrase, typically using all the original letters exactly once. So the original word or phrase is called the subject, and any word or phrase that exactly reproduces the letters in another order is called an anagram. So for example, we have the word restful. In this case, this is the subject, so the original word or phrase. And we can make sure that fluster is an anagram of restful, because we are going to reuse all the letters of the word restful in a different order. So all the letters present in the word fluster is present in the word restful, and this is called anagram. So this is what we are going to implement. As far as the concrete implementation is concerned, it is quite straightforward. So if we have a one-dimensional array of characters representing the first word, and we have another one-dimensional array of characters representing the second word. In this case, the first word is restful, the second word is fluster, and we are going to store all the letters in a one-dimensional array of characters. So these characters are going to represent the first word, and another array of characters will represent the second word. So first of all, if the length of the first string is not equals to the length of the second string, It means that the length of these two words are differ, so we return false, they cannot be anagrams. Then we have to sort the given strings. In this case, the given strings are one-dimensional array of characters. We can sort it with the help of arrays.sort. It is going to have ordo n log n, so linear arithmetic running time complexity. We have to sort the first array, we have to sort the second array of characters. So basically we are going to sort the first word as far as the letters are concerned, and we will sort the second word as far as the letters are concerned, and finally we just have to compare the given letters on a one-by-one basis. So as you can see, we iterate through all the given letters, and if they are not matching, we return false, which means that they are not anagrams. And if all the characters are matching, basically we have found an anagram and we solved our problem in ordo n log n running time complexity. So I'm not sure whether you are familiar with analyzing algorithms, but if we have an ordo n log n algorithm plus an ordo n, so linear running time algorithm, like in this case. So as you can see, sorting has n log n running time, and then this operation is a linear search basically, so it has ordo n running time. The final running time will be ordo n log n, because ordo n log n is a slower algorithm than ordo n. So finally, it is going to be the running time complexity of this algorithm to detect whether two words are anagrams or not. It is just a basic linear search, and it is just a basic sorting procedure. So if we have the two words restful and fluster, let's check whether they are anagrams or not. And as you can see, we return true, which means that these are anagrams. If we change a given character, then these are not going to be anagrams. So this is how we check anagrams. Thanks for watching. In this lecture, we are going to talk about another problem, how to find duplicates in a given one-dimensional array. So the problem is that we want to find duplicates in a one-dimensional array of integers in linear running time complexity, where the integer values within this array are smaller than the length of the array. There are several approaches to solve this issue. First of all, we can use the brute force approach, which means comparing all the items with all the rest, but it has ordo n squared, so quadratic running time. We can do better. For example, we can use hash maps. So we just have to traverse the given array and consider all the items one by one, and try to insert each item in a hash table with the value as the key. If you cannot insert the item, it means that it is a duplicate. So this approach is quite good, but there's a problem that it is not an in-place algorithm. We can do better than this. So the third approach is to use absolute values. With this approach, we can achieve ordo n linear running time that is in place as well. So this is what we are going to consider. Okay, so first of all, we have a one-dimensional array of integers. This array is called capital T. So first we have to consider all the I items of the array T, and we have to check the sign of the T absolute value of T with the index I. So this I is going to be the index of the given items as far as this one-dimensional array is concerned. So we are going to iterate through all the items of the array, and we just have to check the sign of this entity. So the array with the index absolute value of the array at the I index. So the value within the array is going to represent an index again, as you can see. And basically we just have to check the sign. If the sign is positive, then we have to flip the sign. Of course, we just have to negate this entity. Anyways, the sign is negative because we have already flipped the sign earlier in one of the previous iterations, so it means that the given item with index I is a repetition. So basically, that's all about the algorithm. Let's take a look at a concrete example. For example, we have a one-dimensional array 2, 3, 1, 2, 4, 3. as you can see, the values within this array have values smaller than the size of the array. So the size of the array is 1, 2, 3, 4, 5, and 6. As you can see, all the values within the array have a value smaller than 6. Okay, so as far as the algorithm is concerned, we just have to iterate through the array and consider all the items one by one. So the first item is 2. We have to check the sign of this entity, so the array with the index absolute value t with index I, in this case the index is equals to 0, the t0 is, as you can see, the value in the first array block, which is 2, so that's why we have to check whether the item in the array with index 2 is positive or negative. The given item with index 2 is 0, 1, 2, so this is the item which has the value 1, which is greater than 0, so the value at that index is positive. It means we have to flip the sign of this t with index 2. So what does it mean? That 1 is going to be transformed into -1. Then in the next iteration, we have to consider the next item in the array. Again, we have to check whether this value is positive or negative. In this case, the I index is 1. The T1 is 3, as you can see. So we have to check the item with index 3, 0, 1, 2, 3. It is 2, it is a positive number, which means that we have to flip the sign of the T with index 3. So 2 will be transformed into -2. Okay, in the next iteration we have to consider the next item. So again, we have to check whether this entity is positive or negative. What's extremely important that we have to use the absolute value. So the t index 2 is going to be -1, but we have to use the absolute value. That's why it is going to be +1. The item with index 1 is +3, which is a positive number. So again, we just have to flip the sign. Okay, let's consider the next item. In this case, the I index is 3. 0, 1, 2, 3 has the value -2, but we are dealing with the absolute value. That's why we have to check the item with index 2. 0, 1, 2 has the value -1, which is a negative value. It means that the given item we are considering at the moment, so with the yellow color, is a repetition. As you can see, because we have already considered 2, we have found a given repetition. So far we know that number 2 is a duplicate number in this one-dimensional array. Okay, let's keep going. We have to check where the I index is equals to 4. The array value with index 4 is equals to 4, which is positive, so we just have to flip the sign. So +4 will be transformed into -4. And we have to consider the last item. So t with index I equals to 5. It is going to be the item with index 3. 0, 1, 2, 3 has the value -2, which is smaller than 0. So we know again that there is a repetition. So we came to the conclusion that there are several duplicates in this one-dimensional array. To be exact, the number 2 and number 3 are repetitions. So this is how we can check duplicates in a one-dimensional array in linear running time complexity. As you can see, we just have to traverse the whole array once, which means that we consider every single item on a one-by-one basis exactly once. So this is why it is a linear running time complexity algorithm without the need for extra memory. So it is an in-place algorithm, very efficient. So this is how we find duplicates in an array in linear running time complexity. As far as the concrete implementation is concerned, it is quite straightforward after we know the theoretical background. So we just have to consider all the items within this one-dimensional array. So that's why the I index will track the index for the given items in this array, and we just have to check whether this entity is positive or not. If this value is positive, then we have to flip the sign of that given value. Otherwise, we know that it is a repetition, and we just have to print out that the given array item with index I is a repetition. So if we use the same values 2, 3, 1, 2, 4, 3, let's run the algorithm. 2 is a repetition, 3 is a repetition. So we can solve this problem in linear running time complexity quite conveniently with the help of this algorithm. Thanks for watching. In this lecture, we are going to talk about the so-called reservoir sampling problem. So first of all, what is the problem itself? Reservoir sampling is a family of randomized algorithms for randomly choosing a sample of k items from a list containing n items, where n is either a very large or unknown number. Usually, we are dealing with this problem that we don't know the size of the given array. Okay, by the way, this problem is quite often as far as Google or Facebook search results are concerned, that there are billions and billions of search results, and sometimes we are after a sample of k items from these search results. So, choosing a random sample is simple if we know the size of an array. So, for example, we can generate a new random integer within the range 0 and the given bound we have specified, so it returns a uniformly distributed integer between 0 and the bound, but the problem is that we don't know the bound in this case. And this is why reservoir sampling came to be. It is going to solve this problem in ordo n linear running time complexity. So the problem again is that we would like to choose randomly k items from a list containing n items when we do not know the exact size of that given array. Okay, so the algorithm is going to be the following. First, we have to create a distinct array. This is going to be the reservoir array with size k. We are going to copy the first k items from the original array. So this list S containing n items, we are going to copy the first k items to this distinct reservoir array. Then we are going to consider the rest of that given array. So that's why we iterate from k plus 1, because we have already considered the first k items. So that's why we start with k plus 1 up to n. So n is the size of this S array. Basically, it is going to be a for loop, as you can see. So for the I is equals to k plus 1 up to n. We are going to generate a random number in order to be able to deal with probabilities. So with probability k divided by I, where I is the index of the next item in the for loop, we keep the new item, so selecting a random bucket in the array to replace with. With probability 1 minus k divided by I, we ignore the new item. So what does it mean? That we are going to consider all the items as far as the original S array is concerned. And we are going to replace that given item with the index I with a random value from the reservoir array. And this probability is going to be k divided by I. So with probability k divided by I, we keep the new item and we are going to store that given item in the reservoir array, or with probability 1 minus k divided by I, we are going to ignore that given item with index I. Let's take a look at the implementation, and it's going to be clear that first of all we have to use a random, so that's why I instantiated a random as a new random, and it is going to be the reservoir sampling algorithm that's going to solve our problem in ordo n linear running time. So first we create a new array for k items. This is what we have been talking about, that this is the original one-dimensional array, and this k is the number of samples we would like to select at random from the nums one-dimensional array. So first of all, we are going to copy the first k items from the original array to this reservoir array. So that's why I is equals to 0, I less than the reservoir length, I plus plus. We are going to copy the values from the nums array to the reservoir array. and then we consider the items from the original array, of course starting from index k plus 1 because we have already considered the first k items. And then we generate a random number j, and if this j is smaller than k, we are going to store that given item with index I in the reservoir array. So what does it mean? That we are going to store the given number with the given I index with probability k divided by I. So if this j is smaller than k, we are going to override the value in the reservoir array with the nums with index I. So basically the value in the nums one-dimensional array with index I. So this is what we have been talking about exactly, that we are going to keep items with index I from the original array with probability k divided by I, and we are going to discard items from the original array with index I with probability 1 minus k divided by I. And here we are going to show the k random items. So in the end of the algorithm, this one-dimensional reservoir array is going to contain random samples from the original one-dimensional array. Okay, we just have to use a one-dimensional array like this, and I would like to select 5 items at random. So we would like to make sure that the selected items are uniformly distributed. So if we run this algorithm, that this is going to be the solution: 13, 31, 87, 42, and 37. These are going to be uniformly distributed samples with the help of reservoir sampling algorithm. Thanks for watching.